Thanks so much, everyone, for your patience as we had some last-minute technical difficulties, but I'm glad to hear we're a resilient and adaptable bunch. It looks like everyone got the message because we still have a lot of participants. I'm Jeremy Gregory. I'm the Executive Director of the Concrete Sustainability Hub, and welcome to our public webinar series, which have been on a bit of a hiatus recently. And we're fortunate in that as part of the Concrete Sustainability Hub, we also do some collaborations with other colleagues, and one of the best ones we've had so far has been with University of New Brunswick and Michael Thomas on durability-related research. And so he graciously offered to tell us about some of the work that he's been doing there, some of which is related to collaborations here with MIT, and some of it is just independently work that he's been doing for a long time about alkali-silica reactions. So with that, I'm going to turn it over to Mike, and please take it away.
Thank you, Jeremy. So welcome, everyone. I hope you can hear me okay.
Yep.
I certainly have an echo in my headset, so just ask again for people to mute their microphones, phones, or whatever. So thanks for that. Okay, so the title of the webinar today is Development of a Rapid and Reliable ASR Test Method. This work was conducted in collaboration with the MIT Sustainability Hub, and I thought I'd start off by trying to confuse you with this kind of flow chart here, which shows how two of the collaborating universities, that's myself at UNB, with help from Ted Moffat, and Jason Weiss at Oregon State University, have provided inputs to the CSHub. The input from UNB has focused on ASR, and that from OSU is focused on freeze-thaw durability. What I have there in the left-hand side there, these are some of the things that we've been looking at. We've been looking at providing data for the MIT model based on relating expansion of concrete to things like cement chemistry, aggregate mineralogy, temperature, moisture availability, etc. And I wonder if I can ask again. I think somebody just unmuted. I wonder if I can ask people to mute again. And we've done this. We've developed this data in the context of developing a new fill performance test, or I should say laboratory test to simulate fill performance. I know Jeremy asked me at least to at least introduce the phenomena of ASR. So alkali-silica reaction, ASR, is a deterioration process that results in expansion and cracking of the concrete, which can, under certain circumstances, severely reduce the service life of the concrete. What you can see there is a retaining wall with a typical alkali-silica reaction pattern cracking showing up on that retaining wall. What's happening at the microstructural level is this is a reaction between alkali hydroxides that are in the concrete pore solution, originating from the Portland cement component of the concrete, and certain types of reactive silica that are present in certain types of aggregates. In this case here, we have a thin section of concrete that's about 2 millimeters in width of view, so it's quite a large magnification on your screen. And it's showing a reactive chert particle surrounded by the brownish cement paste. The chert particle is expanded and cracked, and what we see in the crack in the aggregate and the crack that emanates out into the surrounding cement paste is the reaction product, the alkali-silica gel, which is absorbed water and expanded. So the three requirements for ASR, or three of the requirements for ASR, are alkalis from the Portland cement, silica from the aggregate, and water to provide the transport and also provide for swelling of the gel as well. ASR affects all types of structures, all types of civil engineering structures, all types of concrete structures. Those exposed to moisture can be vulnerable to ASR if the materials are not selected properly to safeguard against this reaction. The MIT model is focusing on pavement, so I just thought I'd show an example of ASR in concrete pavements. The top left photograph there shows the beginnings of ASR in actually a concrete air-filled apronway. And ASR often begins, the cracking begins at the joints for a number of reasons. One is there's more moisture access there. There's less restraint to expansion there, and there's obviously vehicular traffic loads there because of the sort of wheel loads acting on the joint. Eventually it will spread through the pavement, and the ultimate condition could look something like the bottom right-hand picture. ASR itself will rarely lead to complete deterioration of the concrete, but in combinations with other mechanisms, it can be devastating. In a concrete pavement, the other mechanism is typically freeze-thaw action. With all the cracking that occurs because of the ASR, those cracks become filled with water, undergo freezing cycles, and that can literally rip the pavement apart in a matter of years. So it's very important to select materials to make sure that alkali-silica reaction doesn't happen within the life of the structure. So selecting materials, how do we do that? How do we select the right materials? Well, we have a number of different test methods for testing for the possibility of ASR, and the majority of these involve casting either mortar samples or concrete samples using the materials in question, the materials that are likely to be used on the job, and actually measuring expansion over a period of time. We generally, in most of these tests, we take efforts to accelerate things by either adding additional alkali to the concrete, boosting the alkalis in the concrete, by providing an external solution of alkali, or by increasing the temperature of exposure. And sometimes we do a combination of these things to make ASR happen rapidly in the laboratory. So why develop a new test? There's plenty of test methods out there, and I've listed a few of them there. Unfortunately, the results from different tests are often in disagreement, and sometimes tests give us results that don't match our expectations from the history of field performance of materials. So at this point in time, we don't really have a perfect test for alkali-silica reaction. So there are a number of research organizations that are working to try and develop more reliable testing approaches, and we're just one of those, and this is just one possible approach that we're looking at. If you look at current guidelines, popular guidelines for controlling the risk of ASR in concrete, perhaps one of the most recently developed ones is ASTM C1778, which is kind of a standard practice for examining the risk of ASR and trying to reduce that risk. This approach is based on the AASHTO R80 approach, which in turn was based on the Canadian Standards approach, which has been around since about 2000, but has slowly evolved since that time. So all these approaches have in common a performance-based approach, which essentially uses two test methods. One of these is the accelerated mortar bar test, which is a very rapid test conducted at a relatively high temperature, 176 degrees Fahrenheit. It can give you an answer within 2 weeks, so it's a very popular test for that reason. And then there's the more slowly, longer duration concrete prism test, which, as you can see there, involves using concretes rather than mortars. And this test can take anywhere from 1 year to 2 years to perform, depending on what you're using the test method for. The problem with these tests is they don't correlate very well. There's a disconnect between the two tests, and what you can see there is results from the accelerated test on the vertical axis and results from the concrete test on the horizontal axis, and there really is a very, very poor relationship between the two tests, and very often the outcomes of the test disagree. If you look at the box in the top left, that represents a case where the accelerated test indicates a mixture to be reactive, whereas the concrete test does not. And then the other box at the bottom right is the conflict with the opposite to that. which is where the concrete test indicates reaction, but the accelerated test doesn't. In my experience, based on all the data that I've looked at, looking at different aggregates, these tests can disagree as frequently as 50% of the time in different geographical areas. So it's really quite unfortunate. Of course, this has opened a debate as to which test is right. I'm going to try to respond to this a little bit facetiously by looking at the problem of the ASR and the chicken. You know, we know that if we take an egg from a hen and we incubate that at 38 degrees Celsius, which is the temperature we run the concrete prism test at, we'll end up eventually with a chick. If we instead cook that at 80 degrees Celsius, we end up with a boiled egg. And it really isn't surprising that we get completely different results from these tests very often with certain aggregates. So it's my opinion that with the accelerated tests, we're often going to end up with egg on our faces, if you pardon the pun. We've looked into this a little bit, and I thought I'd share this data with you, although this isn't work conducted under the CSHub. This is some work that we did in response to this problem in New Brunswick. In New Brunswick, about 20 years ago, CanMet tested a whole bunch of New Brunswick aggregates. Can't remember exactly how many aggregates were tested there, but it shows a similar distribution of test data for the concrete test against the mortar bar test. And in this case here, the tests do actually agree only 50% of the time. I think there's something like 30 different aggregates there. And a big concern is the number of times and I should say before I go any further, the concrete test, results of the concrete test agree very well with fill performance. The aggregates that fail the concrete test have given poor fill performance, and the aggregates that pass the concrete test have invariably given good fill performance. So we know there's a good correlation between the concrete test and fill performance, but not so with the mortar bar test. We were intrigued by this, and we looked at some of those aggregates that failed the mortar bar test but passed the concrete test. And I'm going to illustrate this to begin with just two aggregates. Aggregate A, which is reactive in concrete, and aggregate B, which is non-reactive in concrete. If we actually run those in the mortar bar test, they're both reactive. So this sort of kind of highlights the problem. If we actually run the mortar bar test now at different temperatures, what we actually see is that at different temperatures, aggregate A is always reactive regardless of the temperature, but aggregate B is actually very sensitive to the temperature and is not reactive at 38 degrees Celsius. Even if you run it out at 2 years or more, it doesn't react at that lower temperature, and it's a higher temperature that stimulates the reaction. And that just basically shows the long-term expansion as a function of temperature, and you can see that quite clearly on that graph. We tested more than just these two aggregates. Some aggregates behave well, don't expand at either 38 or 60, but do at 80. Some aggregates don't expand even if you go to 80, and then you have aggregates that expand at all the different temperatures, like our aggregate A. And this can be explained entirely based on the solubility of the silica in those aggregates. And what these graphs show here is silica solubility as a function of temperature for aggregates A and B. And what we see for aggregate A is the silica is soluble at all temperatures. It takes longer at 38 for the silica to go into solution, as we might expect. Whereas aggregate B at 38 degrees Celsius, the silica is not soluble, and it's the elevated temperature that renders it soluble. So this is an explanation for why the 80 degree C test actually will show many aggregates to be damaging when in actual fact they're not. It's a function of the reactive silica content. And in the amount of dissolved silica we get as a function of temperature exactly replicates the expansion that we got as a function of temperature. So it does completely explain the role of temperature in giving us a bad result. So if we looked at those test results where we're getting expansion in the mortar bar test, but not in the concrete, and if we run that at 60 degrees Celsius, we see we get much better agreement. We now have to run the test out at 1 year because of a lower temperature to capture everything. And if we run it at 38 degrees Celsius, we get almost complete agreement. But again, we're having to run it out to 1 year because running it at a lower temperature is more reliable, but it takes much longer. So I think that basically highlights one of the problems with ASR testing. One of the best ways of accelerating the reaction and getting a quick answer is to elevate the temperature. But unfortunately, when we elevate the temperature, we're not just changing the kinetics of the reaction, we're changing the thermodynamics too, as some silica forms become soluble at a higher temperature, but not at a lower temperature. Let's go back again and look at some of our test methods. One of the things that I've done in collaboration with a number of my colleagues is actually build field exposure sites where we can actually place large blocks of concrete for different mix formulations out on an exposure site and actually measure the real risk of ASR. It takes many, many years, and I'm not proposing this as a test method, but this is the kind of data that we actually need to act as a benchmark for our new tests, developing tests, to make sure they tell us the right result. So there's a number of these sites in North America and elsewhere. Europe there's been a number of sites developed in Europe too. I'm showing here some of the sites that I've had some involvement with. Top left is the site of University of New Brunswick. We have the University of Texas. Bottom center is Tree Island, Maine. Bottom right is a site developed by Doug Hooton and Chris Rogers in Kingston, Ontario. Mid-right is a site developed by Benoit Fournier at CanMed in Ottawa. Not shown is a site I developed in the UK at the Building Research Establishment. So we're basically, for something like between these sites, we have over 200 different concrete mixtures, and we have expansion data up to 23 years in some cases now. And as I said, this is invaluable in actually benchmarking our rapid laboratory tests. I should also mention there's another site in Toronto that's been developed by Doug Hooton too. So within North America, we have something close to 10 different sites now. This is a graph I'm sure a lot of people have seen. It's unfortunate that to increase any increase in the reliability of a test also ends up increasing the duration of that test. The most reliable thing of all, of course, is field performance. But we know to really be sure about the field performance of a structure with ASR, we have to wait at least 20 years. I mean, there has been cases of ASR manifesting itself after 15 to 20 years. So, 10 to 15 years might not be long enough for field performance, whereas we can get a very quick answer in a couple of weeks using some of our accelerated tests, but unfortunately they very often give us the wrong answer. So let's look at the concrete prism test, which some people see as the holy grail of test methods. It is much more reliable than the accelerated mortar bar test, certainly for identifying aggregate reactivity. But maybe not so much for identifying whether a particular mix will expand or not, whether a particular combination of materials will expand. And I'm kind of demonstrating this here with some data from the UK. Top left there you can see a photograph of a large block, and the top line, the dark blue line, shows the expansion of that block at about 10 years as a function of the alkali in the Portland cement, or the alkali loading in the concrete from the Portland cement. And you can see that we're getting significant expansion even below 5 kilograms of alkali. It was always thought with this aggregate you needed more than 5 kilograms of alkali. Whereas in the concrete version of a test, the same mixture in concrete doesn't expand at, in this case, 4.7 kilos of alkali. So we're getting a disconnect. And it's not just on our site we see that. This is data from the site developed by Doug Hooton and Chris Rogers. And here we have a silicious limestone aggregate, Sprat, which is fairly famous or infamous in ASR terms. The red line shown there shows the expansion of prisms at 2 years. And we find to get expansion of concrete prisms with a 420 kg mix, which is typically used for ASR testing, we need to get the alkali somewhere in excess of 0.7, 0.8%. Whereas in the field, we see expansion, and that's what the blue line shows. We see expansion at lower alkali contents. That was data for the field blocks at 8 years, and here's some more recent data I extracted from a paper from the Austin ICAR conference in 2012, which shows the low alkali cement at 0.44% alkali is showing very significant expansion in the field at 20 years, but nothing happening in the laboratory. I don't want to overemphasize this case, but we're seeing a similar thing in Texas here. And what this is showing here is the expansion of concrete blocks of the University of Texas as a function of the alkali content in the concrete, in this case here, expressed in pounds per cubic yard. If you want to put those in kilograms per meter cube, multiplied by 0.6. And what's alarming here is not only we're getting expansion at less than 3 pounds per cubic yard of alkali, which we always thought was a safe limit, it's taking a very long time to get there, which really makes us have to rethink our exposure site studies, because at 10 years, 8, 9 years, there was no expansion with this concrete mix. Even in Texas, where we have a very high ambient temperature and things really cook. If you look at the high alkali mix, the green line there, it was basically expanding and cracking in 3 months. So you can really see there the impact of alkali content, not just on the amount of expansion that you get, but on the time to the onset of expansion too. This is what the low alkali block looks like, with less than 3 pounds per cubic yard of alkali in it. This is what it looks like, I think, about 2 years ago. And what's interesting here is that 3 of those concrete mixes do not expand in our concrete prism test. They all expand out in the field, but not in the concrete prism test. So this data has all been provided to me by Kevin Folliard and Thano Dramalis, University of Texas, and Thano just sent me these 4 photographs this morning to include. And you can see that the expansion is much worse in the high alkali cement, and it's just beginning in the low alkali cement in the bottom right of that photograph. So it doesn't look too bad at the moment, but as you can see from the expansion curves, things are just beginning. And we would have drawn the wrong conclusions 2 years ago. That just shows the same data, so I'll skip over that. So why is this happening? Well, one of the things we notice when we test concretes, that when we test big blocks out in our exposure site, expansion might take a few years to get going, but it keeps on going long term. In our concrete prism test with the same mix, we get expansion very early on, but it kind of levels out fairly early, and we see less expansion long term. Why is that? And the reason for this is related to alkali leaching, as I'll show you in a minute. This graph here shows again the expansion of one of those large blocks over a 4-year period, and the evolution of the pore solution alkalinity in that same period. And what we see, if we squeeze out the pore solution from the concrete, is we start off with a high alkali content that reduces quickly within a year to a lower alkali content and remains stable beyond that period. And we've often assumed that this represents the threshold for ASR, that once the pore solutions drop to that level of alkali, ASR has stopped. Whereas you can see with the expansion curve, it hasn't stopped. And this means we really have to examine what's happening to the alkalis. And this again is a graph that a drawing I think many of you have seen. But if we actually try to follow what happens with the alkalis in concrete, the alkalis originally reside in the pore solution. Well, they come from the Portland cement and they're quickly pulled out into the pore solution. Most of the alkalis will reside in the pore solution. If we have a reactive aggregate present, we'll form alkali-silica gel, and some of those alkalis get pulled out of the pore solution and get consumed. But the gel will react with any calcium hydroxide in the system and become a calcium-rich gel, releasing the alkalis back to the pore solution. This can be further complicated in some cases by aggregates combining or providing contributing alkalis to the pore solution. So what we really need to be able to test a specific mix for ASR is we need to be able to look at a closed system where all of this can go on, where we're not adding alkalis, we're not removing alkalis from the system, but we're still providing additional moisture. That's the challenge, to provide additional moisture without promoting either leaching of alkalis from the system or providing alkalis to the system. And the problem with our two test methods that we have is, as I'll show in a minute, with the concrete prism test, we result in a situation where we leach out much of the alkalis that are in the pore solution, end up in the bottom of our container that we run the test in. Whereas with the accelerated test, of course, we're providing an infinite source of alkalis to the system. And that, in combination with the high temperature of 176 degrees Fahrenheit, is part of the reason we get erroneous results from that test very often. If we think about what we need for an ideal test, the ideal test, obviously, it has to be reliable. The end box there is it has to be rapid. That's a big challenge, rapid and reliable. We need a test that we can test for job aggregate, unprocessed if possible. It needs to be sensitive to the alkalis provided by the cement, so we shouldn't be augmenting the alkalis. It needs to be able to measure the efficacy of SEMs and even lithium in terms of controlling expansion. The only test that comes close to doing all of these things is fill performance. Fill performance, we can tick every box except, of course, it being rapid. Our concrete prism test, you could argue it's not rapid. 1 year certainly isn't rapid, but it's not sensitive. It's insensitive to the cement alkalis because of a leaching of alkalis during the test. Our mortar bar test, really pretty much the only boxes we can tick are the rapid box and the fact we're testing the job aggregate, but we have to crush that aggregate and grade it, so we're not even testing that aggregate unprocessed. So really this test is proven to be quite unreliable. So coming back to our requirements, one of the ways of trying to maximize expansion without providing a reservoir of alkalis, we want to minimize alkali leaching, we want to maximize moisture availability, and these are often conflicting requirements. And of course, one of the ways of doing this is to have very large samples, such as our blocks on the exposure site, or maybe large blocks in a more controlled system where we can elevate temperature if we want. We've conducted tests like this before in our lab. Again, I'm not suggesting this as a practical test beyond research, but you can certainly minimize the alkali leaching and the alkali addition in a storage condition like this. So our approach with this early work was to use very large samples to minimize leaching and place them in moisture, provide them with access to water, the water being balanced to match the alkali content in the concrete, but having a very small amount of water so that we don't provide a sink for leaching. And that kind of became our sort of proposed lab scale version of this test. We started off with a lab version or smaller scale version by using a system like this where we had a sealed sample, providing it with a small supply of water and having an embedded strain gauge in there so we didn't even have to touch the sample. And we've tried various variations on this test approach to try and, as I say, minimize leaching and minimize supplementing the alkalis as well. Other people have tried similar things. University of Texas, in combination with Texas Department of Transportation, devised their concrete cylinder test, which was essentially a sealed cylinder with water ponded on the top. And again, the cylinder remains almost permanently sealed, so we're providing additional moisture without providing a sink for alkalis. In Japan, they've been experimenting with wrapping the prisms in wet cloth and that wet cloth is pre-soaked with alkalis to try and reduce the leaching potential, and that just shows some of the data from Yamada, which indicates this might be a promising approach. So to the UNB test approach, similar to the large-scale samples I showed you before, what we're doing here is basically taking a almost 6-inch concrete cylinder and placing it in a 6-inch concrete cylinder mold, such that there's about a 2-millimeter annulus between the concrete between the concrete cylinder and the mold, and we backfill this space with a pore solution, which we basically, the recipe for the pore solution we predict based on pore solution test data. So we're using the same solution outside the concrete as we have inside. And the other important consideration here is the actual amount of external water is in the region of about a quarter to a third of the actual amount of pore solution. So any dilution, you're trying to combat dilution anyway by designing the surrounding solution to be the same as a pore solution, but also you've got a very small amount, enough to fuel ASR because you keep topping this up, but you're not going to lead to significant augmentation of the alkalis or significant leaching of the alkalis. That just shows the test procedure. We had to manufacture some cylinders to cast our samples slightly smaller than the molds. That seemed to be cheaper than smaller than the containers. That was cheaper than actually manufacturing the containers for every different test. But that shows the kind of experiment, the test setup. And this just shows how we balance the pore solution or the host solution with the internal pore solution of the concrete. With straight Portland cement mixes, this is easy. We have fly ash, slag, silica fume, metakaolin in there. We have to rely on some of our pore solution data to try and predict that solution concentration. So the only data I'm going to present today is data from the top series of mixer, 100% PC mixers. Our SCM mixers to date have not shown significant expansion despite years of test, and this is unfortunate, but it's consistent with our field experience, where sometimes if you have a fly ash mix, for example, that does expand, and some fly ash mixers do, we have fly ash mixers with 30% fly ash in them that have expanded in the field, but they've taken 15 years to get there. So, in the lab, it might take 3 or 4 years. So that's just unfortunate. What I'm going to show you mainly is data for the Job aggregate here. This is the aggregate that's expanded even down as low as 0.41% in field exposure, but it takes at least 0.7% to cause expansion in the concrete prism test. So what we want to try and do is to develop a test method which gets closer to the real threshold of expansion. That was the objective with our test method. This just shows a data dump here of the different mixes with Job and the different alkali cements. What's shown here is both the concrete prism test at 38 Celsius, which is 100 Fahrenheit, and also our new test with the same combination. And it's interesting here to compare. Here's the concrete prism test at 0.7. Here's our test at 0.7. So we're getting expansion at much lower alkali concentrations, but we're still not really seeing expansion down at the 0.43 or 0.41%. We have seen expansion at 0.52 now, but not at 0.43. So we're still not getting that close to the threshold that we've determined from field experience. This shows at 60 degrees Celsius we do get some acceleration, and you can see this here, the 0.52 is starting to expand, but we're not seeing anything really significant at 0.43 and 0.41 at this time. But remember that these took 10 years to expand in the field. We're only out to 2 years in the laboratory test. And so, if I'm honest, the title of this presentation was a reliable and rapid test, and I think I have to be honest and say, well, this test is not rapid. There's still a question mark around its reliability. I think it's more reliable than the concrete prism test, but whether it's going to offer any significant improvement as is open for debate, and we perhaps need more test results to confirm that. Again, that just shows some of the results just presented in a different form. I actually meant to hide that slide. So if we plot expansion as a function of alkali content, here's the purple line here. These are our blocks in Texas. So we're getting a small amount of expansion, but some expansion at low alkali content. And our data, at least at 60 degrees Celsius in our test, is almost replicating that. It's missing. It's not capturing yet the expansion at very low alkali contents. It's certainly doing a lot better than the concrete prism test. We're hoping that the beyond 1 year, the line at 38 will show expansion at these lower alkali contents. So we're going to have to. In fact, that data is due very soon. So I'll keep you posted on that one. So just to mention what we've been doing with the SEMs is we've chosen, so in all cases here, the test, I should have mentioned this before, the mixes we're testing in the lab are mixes for which we have long-term performance data for. And that's true of the Portland cement only mixes, but also it's true of the SEM mixes. So, and what we've tried to do is to bracket the levels of fly ash or slag that have actually prevented ASR. So in each case here, you note with the Job here, we have mixes with 30 and 56% fly ash. That's because based on in the field, 30% hasn't worked, 56 has. With the Sprat, we've got 20% and 30%. Again, 20% didn't work in the field, but 30 did. We have 50% and 65% slag. 50% hasn't worked on the CanMet site, but I think it has worked on the Kingston site, so that's a bit confusing. And then we have a ternary blend here, which has worked on the Kingston site. And then again with the Spring Hill, 30% hasn't worked and 56% has. Unfortunately, in our lab test, none of these have expanded to date. It's just not long enough. And I'm using the 30% fly ash with the Spring Hill as an example here. Hasn't expanded in the lab, but it didn't expand till about 12 years in the field. So the fact that it hasn't expanded in the lab after 2 years is perhaps, in hindsight, not surprising. We've had cases in the UK where we haven't seen expansion. This is very, very low levels of expansion, but here's some fly ash concrete blocks. These are control specimens here without fly ash. These are mixes with fly ash. And at 15 years, everything was looking pretty good. But by 18 years, some of the mixes have started to expand and developed a little bit of cracking. At 19 years, somebody drove a bulldozer and cleared the site. So unfortunately, we don't actually have any data beyond that time, at least not for those mixes. That just shows the cracking that did develop prior to the bulldozer hitting it. So it's unfortunate we've lost that data, but it does kind of illustrate just how longer term we need to actually study to be sure that these preventive measures are actually working. We have conducted an alkali inventory of our concrete in this new test method to see what's happening to the alkalis. Are they mobilizing? Are they leaching into the surrounding pore solution? The data is a little bit confusing. I'm still trying to make sense of it. What we do know is the alkalis haven't changed that much, but in the host solution, the hydroxyl ion concentration has dropped, but the alkali concentration, the sodium potassium, has remained reasonably stable, which indicates that surrounding solution is carbonating, and it perhaps carbonates to a small extent every time we take the sample out and measure it. So one of our suggested improvements to this test is to try to avoid doing that by perhaps using embedded strain gauges. Anyway, that's where we stand with the alkali inventory. That just shows some of the data there. I don't. It's hard to explain face to face, let alone over the phone. So we're currently writing this up and trying to make sense of it. So where do we stand with our scorecard? Well, the reliability of the test has to be determined because we're still waiting for data. We haven't tested lithium, so we don't know. And unfortunately, even at 60 degrees Celsius, this is not going to provide a rapid solution. We were hoping at 60 we'd be able to overcome the slowness of a 38 degrees Celsius test. But what we didn't take account of is that even at 60, when you have a low alkali system that's high enough to produce expansion, eventually, it's the eventually that kills you. You just have to wait too long. So really, I think one of the biggest challenges that we have is we need to somehow accelerate this to reaction without changing it. So we're still in that situation after this research here. How do we accelerate without changing the reaction? If we want a test method that's capable of testing a specific job mixture, we have to be able to accelerate it without changing it, and I think that's going to be the biggest challenge ahead of us. Thank you.
Thanks so much, Mike. That was super helpful. We definitely have some time for questions. I appreciate you staying within the time limit. And everyone, you're muted, and you can go into WebEx and unmute yourself by clicking on the little microphone on the right. Or if you want, you can send something in the chat box, and we can relay it that way as well. So questions or comments for Mike? Maybe while people are thinking about their questions, I'll start out with one, Mike. We are fortunate enough to have you host us there at UNB and take us on the tour of the Mactaquac Dam, which featured in this presentation a few places, which has suffered quite a bit from ASR. And I wonder if you could just share, just a couple of minutes talking about how they were considering, future options for the dam, considering the fact that this ASR is such a big problem there. They should they rebuild a new one, or should they mitigate it with current measures, that kind of thing?
Yeah. Well, up until 2 years ago, the plan was to replace the concrete structures. The main dam, a kilometer long, the main dam is an earth dam, and there's nothing wrong with that. So the proposal was to replace the concrete structures in 2030. That date was chosen because that's when the turbines and generators have to be replaced. I didn't want to put new equipment in a dysfunctional dam. So that was the plan, and the challenge at that time was in rebuilding. The economy would dictate using the same aggregate because they'd create from the excavation involved. They create the same aggregate. So the challenge until 2 years ago was to try and find a way to prevent expansion with that aggregate. We were looking. The favorite approach was to use fly ash because fly ash is generated here in the province. So we were looking at what would a safe level of fly ash be to control ASR with that aggregate. And one of the problems we faced was what test method do we use to determine that, because the safe level of fly ash depends on the test method you use. So we were looking at a whole range of tests, including large blocks exposed on exposure sites. But 2 years ago, a decision was made not to replace the concrete structures, but to actually try to keep them in service until the dam's 100 years old, which is 2068, which is essentially another 50 years. So there's been a complete change in emphasis, and what we're working on now is not so much trying to prevent ASR in new construction, but we're trying to look at ways of managing the expansion. Well, first of all, trying to look at ways to predict the expansion we're going to get in the future, and try to predict how the behavior of the dam is going to change with that expansion. and focusing on ways to mitigate any deleterious impact of that expansion. So it's been a real shift of gears in the last 2 years, but I have to say it's pretty exciting. It's like one great big laboratory out there, and it's very interesting work.
Yeah, for me, it's kind of fascinating just that obviously you said it has to do with the economics because you have to use the aggregates that you have nearby there. So it kind of shifts this mindset away from how do we prevent ASR to how do we just, we know it's going to happen, how do we mitigate it, which is, just a little bit different mindset.
Yeah, and the economy, so I mean, there's 500,000 cubic meters of concrete there, so that translates to about 350,000 cubic meters of aggregate are going to be required. That's a lot of trucks to ship in, especially when the nearest 100% non-reactive aggregate is about 100 kilometers away. So it's an interesting problem.
Mm-hmm. All right, other questions or comments for Mike?
I have a question. It's Nick Popoff. Hi, Mike. Nice presentation. You showed a slide or a couple slides on solubility of silica, reactive silica in the aggregates, and how in highly reactive aggregates it was more soluble at elevated temperatures, and with relatively non-reactive, I think it was non-reactive, it became soluble at elevated temperatures, right?
Yeah.
Yeah, and what solution were these aggregates residing in? Was it potassium, sodium hydroxide, calcium hydroxide? How did you solubilize them?
We actually followed the quick chemical test for 289.
Okay.
So in that test, you use 80 degrees Celsius. You use a crushed material, and you use 1 mole of sodium hydroxide. So we used that test approach, but we changed the temperature. We ran it at 38, 60, and 80. So.
Okay. And is there any thought that maybe why field versus lab isn't always replicated, because you're not necessarily, when you're casting assessments, you're curing them at normal temperatures first, right? And then you elevate the temperatures, or you have them at lower temperatures. The field concrete will basically, it's going to go at will. And we know that the Texas site blocks basically blow up, 3 times or 4 times as quickly as the blocks that were cast, or the field blocks in CanMet. Is there a temperature element that's critical to understanding, the reactivity mechanism here? And SCM replacements might be dampening that somewhat, and that might be another kind of lever in the mitigation realm?
Yeah, well, when Texas started reporting that a lot of our low alkali mixes started to expand, and then the next thing we started to see concrete expand in Texas that had traditionally satisfactory levels of SEM, you would expect them to work. It was tempting to think, well, that's Texas, it's damn hot down there and everything's different. Maybe we don't need to pay attention to what's happening in Texas. But then, we started to get the data from CanMet, which, the CanMet field exposure site was developed first, but because it's a lot colder in Ottawa, it's taken probably a bit longer to get data. And then in Benoit's site in Ottawa, we're now seeing at 15, 20 years, yes, some low alkali mixes are expanding, and yes, some mixes with 30% fly ash are expanding, 30% Class F fly ash. So the temperature definitely has a big impact on how quickly it happens. I'm not sure within the temperature range that we're looking at, between Ottawa and Texas, it has a big impact on whether it happens or not. It's just, how quickly it happens. We do know if you got really hot, so if you got to 80 degrees Celsius, then that can impact on whether it happens or not. But I think within the temperature range between Ottawa and Texas, what we're seeing is just a matter of time. We're not so much changing the outcome, we're just changing how quickly we get to the outcome. Does that make sense?
Yeah, and I'm just wondering as well, because whenever we're doing temperature predictive modeling, I guess, for temperature rise in concrete, the higher the SCM replacement, the lower the temperature, the ultimate temperature. And maybe that's one preventative mechanism that we've never really considered that should be, one of these levers that we can pull in mitigating when using somewhat reactive aggregates. Okay, and then another question, I don't want to monopolize this, but we always speak about cement alkalis, and we know that alkalis come from different sources and different, SCMs, and we've seen that, but we still keep talking about cement alkalis. Do you foresee the time when we start to, I guess we're trying to do is get a better model, right, or predict it better, but have you ever given thought, or are you guys thinking that maybe it's total alkalis coming from everywhere that we should be considering at some point?
Yeah, well, I think it's available alkalis that we need to consider, and then it comes down to available to what. Because if you look at an available alkali content where you first react everything and then look at what you can leach out into water, then almost all the alkalis and all the cementitious materials are actually available. But that's not really the answer, because you don't get ASR at a pH of 7. So you start to, with the alkalis in the system, they're all available in a sense, but there's also a partition between what's in the pore solution and what's in the hydrate phases. And if you have a sink of alkalis, such as ASR, then it's going to pull alkalis out the pore solution, and some of the alkalis will come out of the hydrates to combat that, but not all of them. And so then you have to start to think about, well, the alkali availability to what kind of solution is important. And so we've done some work in that area, myself and Medhat Shahata, and we showed that at the alkali concentration that you need to drive ASR, which is about a pH of 13.2 or something like that, then really it's the alkalis that are available to that system that are important. And we found that was dependent very much on the actual chemistry of the binder, particularly the calcium, silica, and the calcium and silica content of the binder. That as we put more reactive silica into the binder, pozzolan or slag or something like that, then less of the total alkalis became available to that pore solution. So it certainly shouldn't be all of them, because all of them would prohibit most fly ashes from being used, because almost all fly ashes have a higher alkali content than the Portland cement they're replacing. But they're not all available. So the challenge is to come up with a test method that truly indicates the alkalis that are going to be available for ASR over the lifetime of the structure. And further to that challenge is for the aggregates too. We know many aggregates contribute alkalis. Jeremy just mentioned the Mactaquac Dam. There, we estimate that the amount of alkalis that are available in the aggregate are actually greater than over the life of the structure. They're probably greater than the alkalis contributed in the first place by the Portland cement. So it's a very complex situation that fortunately requires at least 10 years more research, which is what I've got.
Right. Okay. Thanks, Mike.
Other questions for Mike?
Mike, it's Doug Hooton.
Hi, Doug.
I was interested in your UNB test, and you made a couple of comments about, well, one of them was you said that the host solution, a little bit in the 2 millimeter annulus, was carbonating. Why wouldn't you just replace that each time you took a measurement with fresh solution?
And that might be the answer, but then by doing that, you are, in a sense, augmenting the alkalis in the system.
But you said the alkalis hadn't changed; it was just the hydroxyls that had changed.
And that is a potential path forward. That we would do that, and maybe keep it at the alkali concentration required to drive ASR. That is a potential path forward for sure.
And I was thinking about that test where you're trying to match the pore solution with an SCM mix. At what age do you determine that pore solution, because it's going to change over time with SCMs?
Yeah.
If you put fresh concrete in with a later age pore solution, you're going to be pulling stuff. If you do it the other way around, you might be pushing it in.
Yeah, I mean, ideally you'd want a dynamic external solution that
Right.
change in the same way. And we used what we had was either 90-day or 180-day data, which
Okay.
all kinds of plots. So we were using the long-term solution concentration from systems without reactive aggregates.
Mm-hmm.
So it's kind of this, if you like, the long-term buffered pore solution concentration. And beyond about 3 months, we don't see much change in the pore solution if reactive aggregates aren't present, with the exception of silica fume. Whereas I
Might
think
come back,
yeah, some of it starts to creep back out again as that, you know, the original alkali-silica gel you produce converts to CSH. Some of the alkali starts to come back out again.
Thanks.
And it may well do with fly ash, but over a longer time period.
Yeah. Although we thought maybe the alumina had something to do with preventing that from happening.
Yeah, that's right, because we don't see it with metakaolin.
Mm-hmm.
And you know, the work that Karen did at EPFL also shows that alumina has an impact on altering the solubility of the silica too, which is interesting. And that's something you can see with a you know, a calcined clay as well. Is that it not only impacts the pore solution, the impact mainly being based on the silica, but it also changes the solubility of the silica. So there's a lot of interesting stuff going on there that I don't pretend to understand.
Yeah, it's interesting. Because you were talking about the solubility of silica at 80 degrees versus 60 and 38, and at 80 you're going to be pulling all the sulfo-aluminate phases into solution too.
Yeah.
So there's going to be alumina coming out, and I wonder if that affects the silica solubility. Who knows?
Yeah, and one of the things we when we were looking at the accelerated concrete prism test a while back, we found at 60, you know, it didn't change the sodium and potassium concentration of the pore solution, but some of the sodium and potassium was balanced by sulfate as opposed to just hydroxyl ions, which is what you get at 38.
Right.
So yeah, you were definitely pulling sulfates into the solution. Not really aluminates, mainly just the sulfates. The aluminates were still relatively low, higher, but still
low. Yeah.
Yeah, still low.
Thanks.
All right, we still have a couple minutes left since we started a little bit late. Any other questions for Mike? Great. All right. Well, if you want to go back and revisit this, or if you have colleagues you know who missed it, we're going to post the recording to our website, and as long as Mike's okay with it, we'll post the slides there as well. So thanks very much, Mike. This is extremely helpful, and like I said, it's a good representation not only of the work you've been doing, but also some of our collaboration as well. So thank you very much.
Thank you.
All right. Thanks, everyone. Bye-bye.